Hello friends, here we are going to discuss pulse modulation. Pulse modulation is the transition from analog communication to digital communication. In our last video lectures, we have talked about continuous wave modulation. In this, parameters like amplitude, frequency and phase of the high frequency sinusoidal carrier wave are varied instantaneously according to the message signal. For example, amplitude modulation, phase modulation and frequency modulation. But here in this session, we discuss about pulse modulation. In pulse modulation, we consider a train of pulses as a carrier signal. And the parameters like amplitude, duration or position of the pulse train varied in accordance with the message signal. So the definition of pulse modulation is the parameters of the pulse train such as amplitude, duration or position varies in accordance with the message signal, then the process is called pulse modulation. Now, on the basis of classification, pulse modulation is of two types. First is called analog pulse modulation and second is called digital pulse modulation. In both cases, periodic pulse train is used as a carrier signal. So, in analog pulse modulation, some features of each pulse like amplitude, duration or position is varied continuously in accordance with the message signal. Or we can say that in analog pulse modulation, information is transmitted in analog form, but transmission process takes place at discrete time or at discrete samples. And in order to convert continuous time into discrete time, we use sampling process. And accordingly, analog pulse modulation is called continuous wave process. But in digital pulse modulation, the message signal is represented as discrete form in both time and amplitude. And here we use sampling as well as quantization process. Using sampling process, we get discrete time, and in case of quantization process, we get discrete amplitude. So after sampling followed by quantization process, the information is transmitted in digital form, that is a sequence of coded pulse. And the main difference between analog pulse and digital pulse modulation is that in analog pulse there is only sampling process for discrete time, but in digital pulse modulation there is both sampling and quantization process in order to get digital information. That is called digital communication. The examples of analog pulse modulation are PAM, that is called pulse amplitude modulation, and PPM, that is called pulse position modulation. While that of digital pulse modulation, examples are PCM called pulse code modulation, DM that is delta modulation, and DPCM that is called differential pulse code modulation. So we discuss all modulation technique one by one. Here the main point is quantization process that represent message signal in discrete form both in time and amplitude, that is called digital signal. Next, we discuss advantage of using digital systems, or we can say digitization of analog sources. The first point is, as compared to analog system, digital systems are less sensitive to noise. Second point is, digital system make ease to integrate different services. For example, video and soundtrack are combined into the same transmission scheme. According to third point, digital circuits or systems are less sensitive to physical effects such as vibration and temperature. Fourth one is, compression of large data signal is possible only in digital communication. And the last one is, because of advanced digital signal processing technique, storage and manipulation of digital signals become easier. So these are the advantages of using digital systems. So next we are going to discuss first topic of pulse modulation, that is called sampling process. In analog pulse modulation, there is a sampling process. According to this, continuous analog signals such as m function of t get converted into discrete analog signal, taking at sampling instant t equals to nts, where t suffix s is called sampling period. Discrete analog signal is denoted by m function of n into ts. Generally, we take unit sampling period, that is ts equals to 1. So, discrete signal is represented as m function of n. So, t is called continuous time and n is called discrete time. To explain sampling process, we consider any arbitrary message signal mt, that is continuous signal, and its sampled signal is denoted by m del t. Both are analog signals. Only the difference is in time axis. In original signal, time t is in continuous form, while in its sampled version signal, the corresponding sequence of samples are uniformly spaced in time. So, at these sampling instant, that is ts, 2ts, 3ts, we have sample value corresponding to the amplitude of the original signal. And here we consider modulating signal as a band limited signal with FM as a maximum modulating frequency. So in frequency domain, the message spectrum, that is capital M function of f, is band limited between minus FM to plus FM with the bandwidth of FM. Here we take only positive frequencies. So for any arbitrary message signal mt, we consider an arbitrary spectrum denoted by capital M function of f. And in order to convert continuous analog modulating signal into discrete analog signal, we use sampling signal, that is ST. This sampling signal is also called carrier signal. Ideally, impulse train is used as sampling signal, which having a periodic train of impulses at fixed sampling period, that is Ts, and range from minus infinity to plus infinity. But practically, we use periodic pulse train, and the width of each pulse is Tw. These sampling signal having sampling frequency Fs equal to 1 upon Ts, which is called sampling rate. Now, in sampling process, both analog signal mt and periodic unit impulse train st is passed through the multiplier. And at the output of the multiplier, we get sampled signal or discrete signal denoted by m del t. Here the analog signal mt is sampled at uniform rate at every ts second, called sampling period. And here unit impulse train is used as a sampling signal. So the process is called ideal or instantaneous sampling. Now we discuss next topic, that is sampling theorem. As we know that the discrete signals are generated using sampling process, and in order to recover original band limited signal, then we use sampling theorem. So, according to sampling theorem, we can recover original band limited message signal from its sampled version by simply taking sampling frequency Fs always greater than or equal to twice of Fm. Here Fm is called maximum modulating frequency. And this criteria to recover original band limited message signal from its sampled version is called Nyquist rate. So according to Nyquist rate, the sampling frequency must be greater or equals to twice of Fm. Now we explain sampling theorem for the recovery of original message signal in detail. So first we consider any arbitrary baseband or modulating signal MT. In frequency domain, its arbitrary spectrum is capital M function of F that having a bandwidth of FM called modulating frequency. And to obtain sampled version of baseband signal MT, we take a sampled signal, that is ST. This is also called carrier signal. Mathematically, sampled signal ST is equals to sigma n equals to minus infinity to infinity del t minus n ts. Here ts is called sampling period. Here when we put n equals to 0, we get impulse del t, that is at time t equals to 0. Also for values n equals to plus minus 1 plus minus 2 up to infinity, we have periodic impulses. Since sampled signal ST is in time domain, and in order to recover baseband signal MT, our convenient domain is frequency domain. So we do calculations in frequency domain. So we take Fourier transform of ST, that is capital S function of F, and it is equals to F naught summation del F minus n F naught, and taking limit n equals to minus infinity to infinity. In place of F naught, we can write sampling frequency Fs. So sampling frequency is equals to 1 upon Ts. And after multiplying baseband signal MT with sampled signal ST, we get a sampled version of modulating signal, that is M del T, as shown in figure. And its frequency domain spectrum is capital M del function of F. Initially, the spectrum of the baseband signal is capital M function of F, that is centered at 0 frequency, but after sampling process, the sampled signal having periodic spectrum at sampling frequency plus minus Fs plus minus 2 Fs up to infinity, including spectrum at origin. So the sampled analog signal M del T is represented in frequency domain having periodic frequency spectrum from F equals to minus infinity to infinity. Now, in order to recover original spectrum of message signal that is centered around origin with bandwidth of FM, we use low pass filter. So at the receiver side, we use a low pass filter having a cutoff frequency of FM. And according to sampling theorem, the sampling frequency Fs must be greater or equal to twice of the modulating frequency. Then only we recover the original message spectrum that is centered at origin having bandwidth of FM. Now we discuss significance of Nyquist rate. Why sampling frequency Fs is always greater or equals to twice of FM. For this, we consider three cases. First case is when sampling frequency is greater than twice of FM. As we know that modulating frequency FM is the bandwidth of modulating signal, and when we take sampling frequency greater than twice of FM, the low pass filter recover exactly the original spectrum of the baseband signal without any distortion. In second case, we consider sampling frequency equals to twice of FM. Then also we can recover original message signal assuming ideal low pass filter. But when we consider sampling frequency less than twice of FM, that is third case, there occur an aliasing effect. In aliasing effect, the periodic spectrum of the sampled signal get overlapped with each other and we would never recover modulating signal. As sampling frequency is less than twice of FM, the resultant spectrum is called undersampled version and exhibit the aliasing phenomena. And this spectrum also called anti-aliased spectrum. So, in order to get original baseband signal, the sampling frequency must be greater or equals to twice of FM. So, in order to avoid aliasing effect, a low-pass anti-alias filter is used before sampling process. This anti-alias filter attenuates high-frequency component of message signal that is not a part of information-bearing signal. Secondly, the filtered signal, that is output of anti-alias filter, is sampled at a rate slightly higher than the Nyquist rate. Here, capital G function of f is the filtered information signal that is band limited to W. This anti-aliased filter spectrum goes for sampling process with sampling rate of fs greater than twice of W, and we get sampled version. After this, reconstruction filter is used to recover the original baseband signal having bandwidth W. The ideal amplitude response of the reconstruction filter is shown in figure. This reconstruction filter is a low pass kind with the passband between -W to W. The non-zero transition band is limited between +W to Fs minus W, that is for positive frequency. Here Fs is called sampling frequency, that must always be greater than twice of W. Next, we talk about disadvantage of using ideal sampling. As we know that in ideal sampling we use periodic impulse train, and due to very narrow samples the transmitted power is very small, and as a result the sampled pulse may got lost in the noise. And second point is, in practice it is impossible to have pulses of width approaching 0. So the ideal sampling is used only to prove sampling theorem. But in practical sampling process we use periodic pulse of train having width of tau. In practical sampling, the duration of sampling pulse is finite and amplitude of each pulse is also finite. So, the practical sampling techniques are of two types. First is natural sampling and second is called flat top sampling. In natural sampling, the constant amplitude of carrier signal is changed according to the modulating signal, that is shown in figure. But in case of flat top sampling, the constant amplitude of each pulse in sampling signal varies according to the baseband signal, but here the top remains flat with the help of sample and hold circuit. And in practice, generally flat top sampling is used. Here the modulating signal is sampled instantaneously at sampling rate and duration of each sample is constant, that is tau.